Welcome back to the channel. As we move forward with Model 2. In this session, we'll take an in-depth look at probability and statistics as they apply to machine learning. These core concepts provide the essential mathematical framework behind how machines learn from data, make predictions, and improve their performance. Throughout this presentation, we'll explore the fundamental ideas that help us to manage uncertainty, identify data patterns, and validate machine learning techniques. No matter if you're a student, researcher, or practitioner, understanding these concepts will significantly enhance your ability to develop robust, accurate, and interpretable machine learning models. So, let's dive right in. Why probability and statistics matter in ML? Machine learning operates in a world of uncertainty. The data we work with contains noise, outliers, and inherent randomness that must be modeled appropriately. Modeling uncertainty. Probability theory provides the mathematical framework to express and work with uncertainties in data and model predictions, allowing ML systems to make decisions despite incomplete information. Data analysis. Statistical methods enable us to summarize large datasets, identify patterns, and extract meaningful insights that would otherwise remain hidden in the complexity of raw data. Model validation. Statistical tests help us validate model performance, compare different approaches, and ensure that our results are genuinely meaningful rather than the product of random chance. These mathematical tools form the backbone of inference and decision-making in machine learning, allowing algorithms to learn from data and make predictions that account for inherent uncertainties. Probability as a mathematical framework. Probability provides a formal language for describing uncertainty and making predictions. It forms the mathematical foundation upon which machine learning algorithms are built. Sample space represented by omega. The set of all possible outcomes from an experiment or a random process. In machine learning, this might represent all possible data points that could be observed. Events. Subsets of the sample space that we're interested in. For example, the event that a data point belongs to a particular class in a classification problem. Probability measure represented by the symbol p. A function that assigns a value between 0 and 1 to events, representing their likelihood. Machine learning models often output probabilities for different outcomes. Understanding these fundamentals enables us to formalize the learning problem and develop algorithms that can handle the inherent uncertainties in real-world data. Random variables and expectations. Random variables. Functions that map outcomes from the sample space to real numbers, allowing us to work with numerical values rather than abstract events. Expected value. The weighted average of all possible values of a random variable, with weights given by probabilities. This concept is crucial for understanding loss functions in ML. Variance. A measure of how spread out the distribution is from its expected value. Higher variance indicates greater uncertainty in predictions. In machine learning, these concepts help us quantify uncertainty in our data and models. Expected values guide optimization processes, while variance helps us understand the reliability of our predictions and parameters. Probability distributions, overview. Probability distributions describe how probabilities are distributed over different values of a random variable. They are essential for modeling various phenomena in machine learning. Discrete distributions. Used for random variables that can take a countable number of distinct values. Bernoulli, single binary outcome, 0 or 1. Binomial, number of successes in n trials. Poisson, counts of rare events in intervals. Continuous distributions. Used for random variables that can take any value in a range. Uniform, equal probability across a range. Normal, also known as Gaussian, bell-shaped curve. Exponential, modeling time between events. Applications in ML. Modeling noise in data. Prior assumptions in Bayesian methods. Generating synthetic training examples. Building probabilistic models. Each distribution has specific properties that make it suitable for modeling different phenomena in machine learning applications. The normal distribution, the bell curve. 68%. Percentage of data within one standard deviation of the mean. 95%. Percentage of data within 2 standard deviations. 99.7%. Percentage of data within 3 standard deviations. The normal distribution, characterized by its bell-shaped curve, is ubiquitous in machine learning. Its probability density function is given by f of x equals 1 divided by the square root of 2 pi sigma squared, multiplied by the exponential of negative quantity x minus mu squared over 2 sigma squared, where mu represents the mean and sigma the standard deviation. This distribution is foundational to many ML algorithms including Gaussian naive Bayes, Gaussian mixture models, and Gaussian processes. It's often used to model measurement errors, noise in data, and as a prior distribution in Bayesian inference due to its mathematical properties and the central limit theorem. Bayes' theorem, the foundation of machine learning. Bayes' theorem provides a principled way to update our beliefs about hypotheses as we observe new evidence. It forms the foundation of many machine learning algorithms. Mathematical formulation. P of A given B equals P of B given A times P of A, divided by P of B. Interpretation. Updates the prior belief, P of A, to the posterior, P of A given B, using the likelihood, P of B given A. ML applications. Powers naive Bayes, Bayesian networks, and maximum a posteriori estimation. The elegance of Bayes' theorem lies in its ability to incorporate prior knowledge and update it with observed data. In machine learning, this translates to combining our initial assumptions about model parameters with information extracted from training data to arrive at more refined parameter estimates. Bayes' theorem, medical diagnosis example. Medical testing provides an intuitive example of Bayes' theorem in action, demonstrating how base rates and test accuracy affect the interpretation of positive test results. Disease prevalence. The prior probability P of D equals 1% of population has the disease. Test characteristics. Sensitivity, P of T given D equals 99% true positive rate. Specificity, P of T given not D equals 5% false positive rate. Bayesian calculation. P of D given T equals 0.99 times 0.01, divided by 0.99 times 0.01 plus 0.05 times 0.99, which is approximately 0.167. Surprising conclusion. Only about 17% chance of having the disease despite positive test. This counterintuitive result, known as the base rate fallacy, highlights why understanding conditional probability is crucial for correctly interpreting machine learning models, especially when working with imbalanced datasets or rare events. Naive Bayes classification. Naive Bayes is a probabilistic classifier that applies Bayes' theorem with a naive independence assumption between features. Despite this simplification, it performs surprisingly well on many tasks. Mathematical foundation. Classifies by finding the class C that maximizes P of C given X is proportional to P of X given C times P of C, where X is the feature vector and C is the class label. Naive independence assumption. Features are assumed to be conditionally independent given the class, allowing P of X given C to be decomposed as product of P of X sub I given C for each feature X sub I. Advantages. Simple, fast to train and predict, works well with high-dimensional data, and requires relatively little training data. Applications. Text classification, spam detection, sentiment analysis, and medical diagnosis where feature independence is a reasonable approximation. Despite its simplistic assumptions, naive Bayes often outperforms more sophisticated algorithms, especially in text classification tasks where the high dimensionality of the feature space makes the independence assumption more reasonable. Joint, marginal, and conditional probabilities. Understanding different types of probability relationships is crucial for building and interpreting machine learning models, especially those based on probabilistic frameworks. Joint probability. Probability of events A and B occurring together. Marginal probability. Probability of an event regardless of other events. Conditional probability. Probability of an event given another has occurred. Independence. When one event doesn't influence the probability of another. These concepts form the foundation of probabilistic graphical models like Bayesian networks and Markov random fields, which capture dependencies between variables in complex systems. They also underpin generative models that learn the joint distribution P, X, Y, of features X and labels Y, in contrast to discriminative models that learn the probability of Y given X directly. Maximum likelihood estimation is a foundational method for estimating the parameters of a statistical model by finding the parameter values that maximize the likelihood of observing the given data. Observed data. Collect a dataset X equals the set of X sub 1, X sub 2, up to X sub n. Define likelihood. L of theta given X equals P of X given theta equals the product of P of X sub I given theta. Take logarithm. Work with log likelihood for numerical stability. L of theta given X equals the sum of log P of X sub I given theta. Maximize. Find theta that maximizes L of theta given X through calculus or optimization algorithms. MLE forms the basis of many machine learning techniques, including linear and logistic regression. In neural networks, the negative log likelihood often serves as the loss function that is minimized during training. The method provides a principled way to learn from data, though it can sometimes lead to overfitting when working with limited datasets. Statistical significance and p-values. Statistical significance helps determine whether observed effects in data are likely real or merely due to random chance. This concept is crucial for interpreting experimental results in machine learning. Defining hypotheses. Null hypothesis H0 versus alternative hypothesis H1. Computing p-value. Probability of observing the result, or more extreme, under H0. Drawing conclusions. Reject or fail to reject the null hypothesis based on evidence. The p-value quantifies the strength of evidence against the null hypothesis. A small p-value, typically less than 0.05, suggests that the observed data would be unlikely if the null hypothesis were true, providing evidence to reject it in favor of the alternative hypothesis. In machine learning, statistical significance testing is used for feature selection, model comparison, and validating that performance improvements are not just due to random variation in the data. However, it's important to remember that statistical significance doesn't necessarily imply practical significance or causality. Hypothesis testing framework. Hypothesis testing provides a structured framework for making decisions based on data. It follows a systematic procedure to draw conclusions while controlling the risk of incorrect inferences. Step 1. Define hypotheses. Formulate null hypothesis H0, status quo, and alternative hypothesis H1, what you're testing for. Step 2. Choose significance level. Select alpha, typically 0.05, which represents the acceptable risk of type 1 error, false positive. Step 3. Compute test statistic. Calculate an appropriate test statistic, for example, z-score, t-statistic, from the data. Step 4. Determine p-value. Calculate the probability of observing the test statistic, or more extreme, under H0. Step 5. Draw conclusion. Reject H0 if p is less than alpha, otherwise, fail to reject H0. In machine learning, this framework helps researchers systematically evaluate feature importance, compare model performance, and validate experimental results against chance explanations. A/B testing in machine learning. A/B testing applies hypothesis testing to compare two variants of a model or system. It's widely used to make data-driven decisions about model improvements, feature engineering, and algorithmic changes. Experiment design. Define the hypothesis, determine sample size requirements, and plan how users or data points will be randomly assigned to variance A and B or establish metrics to measure success before beginning the experiment. Implementation and data collection. Deploy both variants simultaneously, ensuring proper randomization and isolation. Collect data on relevant performance metrics while minimizing external factors that could confound results. Statistical analysis. Analyze the collected data using appropriate statistical tests. Calculate p-values to determine if observed differences between variants are statistically significant or likely due to random chance. Decision making. Based on statistical results and business context, decide whether to implement the new variant, continue with the current version, or conduct further testing with refinements. This methodical approach ensures that changes to machine learning systems are verified to actually improve performance rather than appearing beneficial due to random variation or selection bias. Type 1 and Type 2 errors. When performing hypothesis tests, two types of errors can occur. Understanding these errors is crucial for interpreting test results and setting appropriate thresholds in machine learning models. Type 1 error, false positive. Rejecting the null hypothesis when it is actually true. This occurs with probability alpha, significance level. In machine learning, this might mean concluding a feature is important when it isn't, or that a model improvement is significant when it's just random variation. Type 2 error, false negative. Failing to reject the null hypothesis when it is actually false. This occurs with probability beta, and 1 minus beta is the power of the test. In ML, this might mean failing to detect that a feature is important or missing a genuine improvement in model performance. Trade-off relationship. There's an inherent trade-off between these errors. Reducing one typically increases the other for a given sample size. Increasing sample size can reduce both errors simultaneously, but often at increased computational or data collection cost. This concept extends directly to classification problems in machine learning, where false positives and false negatives must be balanced according to the specific requirements and costs associated with each type of error in the application domain. Confidence intervals. Confidence intervals provide a range of plausible values for a population parameter, based on a sample statistic. They quantify the uncertainty in our estimates and are widely used in machine learning to evaluate model performance. A confidence interval is constructed as point estimate plus or minus margin of error, where the margin of error depends on the desired confidence level, the standard error, and the appropriate critical value from the relevant distribution, typically Z or T. In machine learning, confidence intervals help assess the reliability of model performance metrics. For example, a 95% confidence interval for a model's accuracy might be 87% plus or minus margin 3%, indicating that with repeated sampling, about 95% of such intervals would contain the true accuracy. Wider intervals indicate greater uncertainty, often due to limited test data. Descriptive statistics for data exploration. Before applying machine learning algorithms, it's essential to understand the characteristics of your dataset through descriptive statistics. These measures help identify patterns, outliers, and potential issues that might affect model performance. Measures of central tendency. Mean, the average value, sensitive to outliers. Median, the middle value, robust to outliers. Mode, the most frequent value. These measures help identify the typical values in your data, which can guide feature scaling and normalization strategies. Measures of dispersion. Range, the difference between maximum and minimum values. Variance, average squared deviation from the mean. Standard deviation, square root of variance. Interquartile range, range of the middle 50% of data. These measures quantify data spread and variability, helping identify features with high information content. Distribution characteristics. Skewness, asymmetry of the distribution. Kurtosis. Tailedness or peakedness. Quantiles, values that divide the data into equal portions. These help identify non-normal distributions that might require transformation before modeling. Thorough exploratory data analysis using these statistics can reveal insights that inform feature engineering, algorithm selection, and hyperparameter tuning decisions. Correlation and covariance. Understanding relationships between variables is crucial for feature selection, dimensionality reduction, and interpreting model behavior. Correlation and covariance provide mathematical tools to quantify these relationships. Covariance measures how two variables change together, but its scale depends on the units of the variables. Covariance between x and y equals x minus mu sub x times y minus mu sub y. Correlation normalizes this relationship to a value between -1 and +1, rho equals covariance of x and y divided by sigma sub x times sigma sub y. In machine learning, these metrics help identify redundant features, high correlation, detect potential multicollinearity problems in linear models, guide feature selection, and inform techniques like principal component analysis. However, they only capture linear relationships. More sophisticated methods may be needed for complex, nonlinear dependencies. Cross-validation, statistical rigor in model evaluation. Cross-validation is a statistical technique that provides a more robust evaluation of model performance than a single train test split. It helps estimate how well a model will generalize to new, unseen data. Split data. Divide the dataset into k equal-sized folds. Iterate k times. Use each fold once as validation set while training on others. Compute metrics. Calculate performance statistics for each iteration. Average results. Final estimate is the average across all k validation sets. Common variations include k-fold cross-validation, typically k equals 5 or k equals 10, stratified k-fold, preserves class proportions, leave one out, extreme case where k equals n, and nested cross-validation for hyperparameter tuning. The technique provides not just a point estimate of performance but also its variance, giving insight into the model's stability across different data subsets. Cross-validation helps detect overfitting, compare different algorithms fairly, and make more reliable performance claims, though it comes at the cost of increased computational requirements as models must be trained k times. Practical applications and future directions. As we conclude our exploration of probability and statistics in machine learning, let's consider how these concepts manifest in real-world applications and where the field is heading. Healthcare. Bayesian models provide uncertainty estimates for diagnoses, crucial for clinical decision-making. Statistical hypothesis testing validates the efficacy of ML-based treatment recommendations against standard approaches. Autonomous systems. Probabilistic frameworks enable robots and autonomous vehicles to make decisions under uncertainty. Confidence intervals around trajectory predictions inform safety margins and risk assessments. Finance. Statistical methods quantify risk and uncertainty in financial forecasts. Hypothesis testing helps identify significant market signals from noise, while probabilistic models capture complex dependencies between assets. Future directions include increasingly sophisticated Bayesian deep learning methods that combine the flexibility of neural networks with principled uncertainty quantification, causal inference techniques that go beyond correlation to identify true causal relationships, and novel statistical frameworks for fairness and interpretability in machine learning systems. Gratitude and path forward. Thank you for your active participation in Module 2 on the mathematics behind machine learning. Your engagement has been invaluable to our collective learning journey. We're now set to advance to Module 3, which will focus on supervised learning, where we'll explore essential topics such as regression analysis and classification techniques in the upcoming sessions. As we progress toward the conclusion of the course, we'll also cover practical Python applications in AI and machine learning. To stay updated on our educational content and future offerings, we invite you to subscribe, like, share, and remain engaged with our learning resources.